So, after completion of first law of thermodynamics, today we discuss about second law of thermodynamics. Okay. While discussing about first law of thermodynamics, I have just given some pointers or hints, like because of second law of thermodynamics, uh, certain things cannot happen, like even if it is true as per first law of thermodynamics. Okay. So first law of thermodynamics is what? It is nothing but law of conservation of energy, right? Suppose we are saying first law is what? Del Q is equal to del U plus del W, right? So this is nothing but uh, uh, law of conservation of energy. Okay. So that is first law, right? Just a recap. Then we said we studied about the heat engine. Then we studied about the refrigerator. Okay. So I was telling in heat engine, the efficiency can never be equal to 1. The efficiency can never be 100%. Efficiency 1 means 100%. So whatever it may be, in a heat engine, the efficiency can never be 100%. That means, like say you have a in heat engine, we had studied that we have a reservoir, right? We have a reservoir, we have a source or reservoir source, and then we have a sink. Then we have this working substance going through a cyclic process. Then we are taking some heat, we are giving some heat. Okay, and then in turn, the heat engine is producing some work. So you are from source at temperature T1, you are taking heat Q1, and you are throwing away some heat to the sink at temperature T2. Okay, and you are giving away some heat Q. You are giving away some heat Q2. You are giving away some heat Q. So, uh, uh, as per second law of thermodynamics, in a heat engine, this efficiency can never be equal to 1. When the heat efficiency will become equal to 1, we further writing that W as Q1 minus Q2, right? So we know W is equal to uh, like Q1 minus Q2 will be in a like in a reversible process, del U is equal to 0. Sorry, in a cyclic process, del U is equal to 0. So del W, W is equal to del Q. Okay, so W is nothing but your Q1 minus Q2, right? That is your del Q, right? So, so this efficiency is Q1 minus Q2 by Q1, okay? Or otherwise, it can be written as 1 minus Q2 by Q1. So Q2 is the heat thrown away or the heat rejected to the sink, and Q1 is the heat extracted, like heat taken away from the source or the reservoir. Okay. So this efficiency, if this efficiency has to be 1 or 100%, that means this term has to be 0, right? Q2 minus Q2 by Q1 has to be 0. So for Q2 by Q1 to be equal to 0, your Q2 has to be equal to 0. So if Q2 is equal to 0, or if the heat thrown away to the sink is equal to 0, then only efficiency will become equal to 1. So, which is not possible as per law of nature. So that's what is the corresponding statement is called Kelvin Planck statement. Okay, the statement made by scientist Kelvin Planck about heat engine uh, um, in relation to second law of thermodynamics. So, what statement scientist Kelvin Planck made? No process is possible Okay. No process is possible where heat engines adjust heat and completely convert it into work. Okay. So that means what is saying, like if you take Q1, you take Q1 and completely convert it into work. Not possible. Okay. So that means you take Q1, okay, and your W becomes equal to Q1. Your W become equal to Q1. Not possible. W means the means or Q1 becomes equal to W. Not possible. You cannot take Q1 and this is your W. Okay. So this is your Q1, this is your Q2, this is your Q2. So you cannot take Q1, the heat, and completely convert it into one. Impossible. That is like making the efficiency of heat engine 100% or 1. So, so no process as per Kelvin Planck statement. This is important. What is Kelvin Planck statement? No process is possible where that is related to heat engine. Kelvin Planck statement is related to heat engine. So no process is possible where heat engine absorbs heat and completely convert it into work. So you cannot take a heat and completely convert it into work. Efficiency can never be 100%. You have to throw some heat to the surrounding. That's what I was telling about the petrol engine, or I was telling about the diesel engine. Okay, so you take some heat that Q1 from the fuel, the petrol or diesel or whatever. Suppose you are taking using 1 liter of petrol. Okay, petrol has some calorific value. So whatever its calorific value, 1 liter of petrol, if you measure the kinetic energy of the wheel, and then how much is the finally out of that calorific value, how much is the work got done? That can never be equal. That means in the heat engine or the internal combustion engine, finally it is sucking the air, then compressing the air, then there is a power stroke, and there is a exhaust. So during that exhaust, what is showing? The surrounding becomes your sink. Okay. So so it is throwing away some gas and some heat Q2 is thrown to the surrounding. So you have to throw some heat to the surrounding. It can never happen that Q2 will become equal to 0. Some heat has to go. Okay, so there will be some energy still left with this thing. Okay. Similarly, in our aircraft engine, so there we are using gasoline, that aviation turbine fuel uh, as the uh, that's the fuel. Okay, so there also we take air. The aircraft takes air from the atmosphere, and then air and fuel get mixed. And then that combustion takes place, temperature and pressure rises, then it get expanded in the turbine. So after turbine, it goes through a nozzle, and that nozzle is something where the pressure energy gets converted into velocity energy. So you'll get high velocity jet gas. Okay. So what is happening here? You will suck some air at velocity V1, which is nothing but the aircraft velocity. Suppose the aircraft is moving through a steel layer. That means at what velocity air will enter? At aircraft velocity. So it will enter at some velocity, and then it will go through the nozzle at the exhaust. It will go away at a bigger velocity. So, as per second law of Newton, that rate of change of momentum is equal to force. So, because of the differential velocity at the entry of the aircraft and exit of the aircraft, which is nothing but the exit of the nozzle, you are getting some force, which is nothing but your thrust. So, there in the Newton's third law applies. Okay, every action has equal and opposite reaction. When a jet is going out at a very high velocity, that means it will create a reaction, and that reaction, like the jet going away rearward with a certain velocity, it will give a push. It will give a forward push to the engine. Okay, If the engine is giving a forward, is pushed forward, after all that engine is connected to an aircraft. So that force will get transferred to the aircraft. So the aircraft will start moving in the forward direction. So when the jet gas moves in the rearward direction, the aircraft moves in the forward direction. So that Newton's third law applies there. So even for any rocket and other things, different stages of a rocket you might have seen, the rocket that is being launched, it will have multiple stage, first stage, second stage, third stage. So the more and more, uh, uh, so you can see a exhaust gas is coming out and it is moving forward. Its velocity keeps on increasing, and there is a time when it reaches the escape velocity and it can escape the Earth atmosphere and it can be placed in the moon orbit or whatever. So that is also third law of Newton or whatever. Okay. So I am deviating from the actual topic. So let us discuss about second law. So second law, you can explain second law with relation to two things. One is heat engine, other one is refrigerator. So with regard to the heat engine, we have the Kelvin-Planck statement, which tells that no process is possible where heat engine absorbs heat and completely convert it into work. Not possible, 100% efficiency, not possible. That is Kelvin-Planck statement. Similarly, coming to refrigerator or heat pump. Okay. So in the refrigerator, we are more worried about Q2. Okay. Whereas in heat pump, we are more worried about Q1. Okay. So in refrigerator, we are concentrating on the volume inside of the refrigerator. That is our area of concentration. Whereas in case of a heat pump, we are more about the room or the surrounding. Okay. So we were discussing about say refrigerator. So you have same thing, only the lines will get reversed. Direction gets reversed. Okay. So this is this, this is this. So this is your surrounding, and this is your let us say refrigerator. So your refrigerator chamber. Okay. Refrigerator chamber at temperature T2. This is refrigerator chamber at temperature T2, and this is your room. Okay. This is your room at temperature T1. Okay. So the in heat engine, like maybe in heat engine, we would say in heat engine, what is happening actually? You have a reservoir, you have a working substance, you have a sink. So you take heat Q1, throw some heat to the surrounding Q2, and do some work W. That is nothing but your heat engine. When refrigerator, what is happening? These lines are just getting reversed. Okay. So you are taking heat. So you are you are taking heat Q2 from the refrigerator chamber. You are throwing away heat to the outside the room, and you are using some work to do that. It means you means throwing away heat from a cold region to a hot region is not is against the law of nature. So if you want to go against the law of nature, you have to do some work. For example, like water. So you water is at a certain height. If you want to take water to a higher height, it is not the law of nature. So you have to spend some work. So similarly, in thermal engineering, like if you want to take heat from a colder region to a hotter region, it is not possible. You have to spend some work. So you might have studied about three ways of heat transmission. That is conduction, convection, and radiation. So always conduction happens from, like suppose you have a iron rod or a copper rod. So the hot end is at temperature T1, the cold end is at temperature T2. So there is we have studied that okay, if the length of the rod is L, if the thermal conductivity is K, area of cross section is A, and if the difference between temperature between two ends of the iron rod is delta T, then heat transfer is equal to Ka delta T by L. That's what we have studied, no? Do you remember? Like heat conducted is equal to thermal conductivity of the material, area of cross section of that particular rod, and Ka delta T, the temperature difference. Higher is the temperature difference, more is the heat transfer, and L is the length of the rod. Okay, so that's the heat transfer. Similarly, we have studied about convection, the natural convection or the forced convection, and we have studied about the radiation, like the transmission of heat from the sun to the earth. So it does not require any medium. Those are electromagnetic waves in radiation. Okay. So all that what is happening, it is heat is getting transferred from a hotter region to a colder region. But in refrigeration, reverse is happening. So if something reverse is happening, you have to spend some energy. If you are doing something against the law of nature, you have to spend some energy. So, like say, a fruit is falling from the tree. It is law of nature. From higher height, it will come to the lesser height because of the gravitational force. Something some gravitational force is acting and it is trying to pull down everything. But if you want to take that fruit again back to the that particular height, you have to spend some energy. So that's what is happening. Is the similar principle in thermal engineering. Heat, if you want to take from the colder region to a hotter region, you have to do some work. Okay, that is the with relation to refrigerator. That is the statement. So there are two statements. One is with relation to heat engine. Another statement is with relation to refrigerator or heat pump. So that is the second statement is Clausius, Science Clausius statement, where says no process is possible where heat get transferred from a cooler object to hotter object without help of external work. That's the thing we are saying. So we in heat engine we have discussed something which is the efficiency. Whereas in refrigerator or heat pump, that term is called coefficient of performance or the COP. So if it is a fridge or refrigerator, it is Q2 by W. Or if it is a air conditioning also. So air conditioning principle of application, principle of operation is similar to that of refrigerator. Okay. So if you are taking away some heat from the room in the air conditioning, what you are doing, you are cooling the whole room. Okay. So the same things components are there: compressor, evaporator, condenser, throttle valve. Those four components are there in air conditioning also. So in air conditioning, what you are doing, you are just throwing away, like making the room cool. So whole room you are cooling it. You are taking some heat from the room and throwing away toward outside of the room. So that is you are taking heat Q2 from the room or the refrigerator chamber by doing some work, which is nothing but the compressor work, and you are throwing it away Q1 to the surrounding. So, so Clausius statement is in relation to the refrigerator or heat pump. And in heat pump, it is not Q2 by W, instead it is Q1 by W. Because in heat pump, your concentration area is where you are throwing the heat. Okay. So, for example, in cooler countries, you want to heat a room. Okay. So, in that case, how much heat you are throwing to the room? So, Q1 is important there. Okay. So, in refrigeration, a refrigerator, the cooler chamber is important. In heat pump, the hotter area or hotter room, you want to heat a portion of a building. Okay, so that portion, you from the rest of the building, that portion of the building which you are heating, that Q1 is important there. Whereas in case of refrigerator, Q2 is important. So coefficient of performance is equal to Q2 by W for a fridge, Q1 by W for a heat pump. Okay. So no process is possible where heat get transferred from a cooler object to hotter object without the help of external work. Okay. So this is with respect to refrigerator. So You cannot throw heat from a cooler object to hotter object without external work. Okay, that is Clausius statement. And Kelvin Planck statement is you cannot take heat and completely convert it into work. Efficiency cannot be equal to 1, and coefficient of performance can never be equal to infinity. Remember that it cannot become equal to infinity. That means you are telling you have to take some work. If you don't take any work, that means this term will become zero. If this term becomes zero, that means COP or coefficient of performance becomes infinity, which is not possible. Okay. So in nutshell, that is second law of thermodynamics. It's a law of nature. Okay. So next we'll be discussing about reversible process, irreversible process, and then the Carnot cycle, how much of work done and all the efficiency of Carnot engine. That will be discussing in the next discussion. Okay, understood? Yes. Okay, so just I'll send this snapshot to you so that you can refer in future.